So the next question, of course, is that of these four, I'm going to tell you one of them is not knotted. In other words, there's a way for us to pull on the strands of this to just get us a nice unknotted circle that knot theorists actually call the unknot. Right? So we can get an unknot from one of these four by pulling on the strands. So my first question, of course, is without touching the knots, can we figure out which one? So chew that one over. Feel free to do so collaboratively if you wish. Bounce some ideas off of one another. If you've got these four diagrams on a page, maybe we'll look at the diagrams as well. I'm actually going to create my own diagrams for these two that we can keep on the board. In order to answer this question about which of these four knots is not knotted, you all went through some imaginative geometry, some like, what would we call it, like speculative manipulation, right? Because you can't touch them. So you just imagine yourself kind of moving strands around, reducing numbers of crossings. And something that Michelle just pointed out was that we had before identified a dull pair of crossings in K2 right there, right? This pair was dull because we can just take this strand and move it to the left of the other strand, and it's like it wasn't even there, and we've reduced the number of crossings by 2. But there's also other types of dull crossings that we notice in here, particularly these loops up here at the top of K3, right? If we could just pick this up and sort of untwist it, we could get rid of those as dull crossings as well. We just have to rotate this crossing around, and that's boring. That's not important to the fundamental structure of the knot either. If we could pick it up, we could untwist it, and we wouldn't have to cut the knot and change fundamentally the kind of knot that it is. Are there any other different kinds of dull crossings that you can spot in these four diagrams that are different than the two that we have highlighted here?
Well, I guess not.
Here's an over-over.
With an under-under, then the other one is over.
With an under-under, the other one is over-over, right? So right here, this example, this under-under, right, would be the same as this over-over, right? It's the same as the two pair of crossings. But that's a great question. Is that different? No. Looking at it from a different perspective, it's the same. Right? So there are two kinds of dull crossings. So looking at K1, we have this sort of under loop up here at the top. So we could just pull that whole thing down underneath this strand and reduce these crossings. The other way to think about that, and I'm secretly doing this for a reason, the other way to think about that is I could take this strand. Rather than moving the loop, I could move the strand down and past this crossing, right? So that instead what we would end up with, let me see if I can do this. Whoops. What we'd end up with instead, close up those crossings, and then draw this down here, and it was under before, right? So we could just move that down, right? So that it's now, it looks like it's changing the ordering of the crossing somehow, but really it shouldn't matter to the fundamental structure of the knot. So somehow that's another thing that we can do to change the ordering of crossings without changing the kind of knot that we have. And so that too is kind of a dull thing. Maybe rather than thinking about them as dull crossings, we can think about them as dull changes that we can make to the diagram for a knot that keeps the kind of knot, but it changes how we draw the diagram. One of those dull changes was the change that we made here. I don't want to use a dotted line because it looks like I've got weird numbers of crossings. Maybe I'll just use a fainter line. So the move that we just did was this one. So that's a dull move, right? It takes what used to be a couple of crossings up here and just moves them down past that other crossing. The move that we would do here with this dull over crossing is we would just move it inward. So if we have an over or we have an under, we can just move that whole loop onto the other side of the strand, reduce our numbers of crossings. And then what do we do with this twist that's dull, that doesn't change the kind of knot that we're working with? With the dull crossing, all we would do is just untwist it, and what we would end up with. So there are three dull things that we can do with a knot diagram, where we actually make the diagram simpler. Well, in the case of K1, we're not really making it simpler, but the one that we did to K2 and the one we did to K3, they are making the knot diagram simpler by reducing the number of crossings. Right? And yet, we're all in agreement that those dull things don't actually change what knot it is that we're working with. I could just come right up here to K3 and just do that. I haven't changed the type of knot that we have, but I have made the diagram simpler. Okay? So if we think of kind of what it means to simplify a knot, maybe these are three things that we can do to simplify a knot diagram, right? To try and get it closer into its lowest terms. It's a valid question to ask, are there other things we could do to a knot diagram besides these three things that could make the diagram simpler without changing the knot that's underneath? And that is a hard knot theory question to answer. In part because it requires us to really have a firm grasp about what it means for two knots to be the same. And or it means that we need to have some way of knowing that any other thing that we can do to a knot diagram could perhaps be built out of one of these three dull maneuvers, right? That maybe there is some exotic other thing I can do to a diagram, but maybe I can just do the same thing by some succession of these dull things. Right? So are these three things enough to build all the dull ways that we can change a knot projection? But let's go through, because you all predicted that which one of these four was the unknot? K3. Let's see if we can use these three maneuvers to completely demonstrate that K3 is unknotted. Right? If we can, then that must mean that K3 is in fact an unknot, despite the fact that its diagram is really complicated. If these dull maneuvers don't actually matter to the knot itself, then if I use them, I'm not changing what knot we have, I'm only changing the diagram. So let's simplify. Right? We did one untwist up here on top. Let's do another. Right? That one right there is a dull crossing, so let's just get rid of it and smooth that out. Still the same knot. All right, what other dull maneuver can I do here?
Pull the loop that's going up.
This little loop right here, right. So this is an under-under, or look at it from the other strand. It's an over-over, right? I can just pull this loop out from underneath that strand. That's this dull maneuver from over there. So let's do that. This little strand goes away, and then we just close up that one down there on the bottom. We've knocked out two more crossings. Right, now we can untwist this one right here, and then that goes away. Untwist this. Hold on, don't want to screw that up. If I untwist that, right, it's just the same as closing that up there, right? And then I just have one untwisting left, and I have an unknot. So K3 is an unknot, and all we had to do to demonstrate that was a sequence of, in fact, just two of these types of dull maneuvers to my knot diagram, right? A little bit of untwisting, a little bit of pulling loops out from underneath other strands, and that's all it took. And we could show that K3 is the unknot. Cool. What about the others? Are we sure that none of the others, are you going to take my word for it, that 1, 2, and 4 are not, in fact, unknotted, that they are essentially knotted? What I'd like for you to do next, I guess, is try and simplify your diagrams, if you can. If you had K1, K2, or K4, do this process and see if you can find a simpler way to depict these other three knots. What is the lowest terms? So the task was to take these four knot diagrams and to simplify them, reduce the number of crossings, use those dull maneuvers that we decided didn't matter to try and reduce the number of crossings as much as possible. For K4, we started with 3 crossings. You simplify it, how many crossings does it have?
Still 3.
Yeah, we can't really do anything with this one. This one is already in its lowest terms. So here's a question. Can I draw a knot with 2 crossings? Kind of want to get a blank screen real quick and pick up on that question. Is it possible to draw a knot with just 2 crossings? What would it look like? Right, so if we just draw a diagram that has only 1 crossing, then according to our most basic of these dull maneuvers, we can just untwist this loop and it becomes an unknot. No matter whether this was an overcrossing here or an undercrossing here, we'll be able to do that. Just untwist it, it becomes an unknot. I use this little symbol here as an equal sign with one of the lines being a twiddle as an equivalent symbol for knots. We're going to hang on to that, talk a little bit more about what it means more specifically later in the course. But yeah, any knot diagram with only 1 crossing is an unknot. There are only 2 possibilities for diagrams with 2 crossings. Both of them are also unknots, right? We could take and untwist this part and that part separately in each case to show that it's the unknot. Or in the second case, we can use the other dull maneuver, the one where we pull this undercrossing underneath, right, to the other side of that strand to show that it's the unknot as well. Right? So 1 crossing is always boring. 2 crossings is always boring. But somehow, the diagram in the previous slide, K4, it's got 3 crossings, and no matter how hard you tried, you couldn't unknot that one, right? We couldn't even reduce the number of crossings in this diagram. So that is essentially a knot, and somehow, because it's got the lowest number of crossings that we can get for something that's actually knotted, it feels like it should be a building block of something, right? The simplest knot that we can draw that's not trivial. This knot is called a trefoil. It's the knot that actually makes the logo in my little website, the book in the corner. There are a number of different ways to present a trefoil. This one kind of makes it look like it's a figure 8 twist in the middle, and then it has the ears on the outside. You can draw it in a variety of other ways. So trefoil is somehow the most basic, simplest knot that we can draw, lowest numbers of crossings. All right, so how about K1 and K2? Let me ask you first, how many crossings did you get down to when you had K1 and K2 into their lowest terms? Well, let's make some progress on this by doing the one dull maneuver to move this strand over. Let me recreate the diagram with that modification. So now it just goes like that, and then it breaks, comes around this way. But then that now comes around to the outside, right? And this way, that way, cross over there, under here, and under there. So I think this is where we land after we do that dull maneuver, and we have still 1, 2, 3, 4 crossings. Right, so the question is, can we make this simpler somehow? So in the process of actually touching these knots, we figured out that there might be a nice way to put them into some kind of a standard position, right, where we kind of pulled all the twists into the middle, and then we have these 2 sort of vertical sides on the outside. And if we can isolate the twists in that way, maybe that's going to give us a much clearer comparison between the various knots to figure out if they're the same. When we did that with K4 and with K1, we found out that actually those 2 diagrams are exactly the same. The same types of crossings arranged in the same order and the same number, right? So K1 and K4 can be made to have the same knot diagram. But K2, this is where we ran into some kerfuffle. Maybe we'll call it kerfuffle. If I try and draw the diagram for K2, what I get is something that looks like this. I'm drawing in real time again. Similar, but it's not quite the same.
Right.
Over, and then it breaks, and then it comes around this way, and then it goes up. Crossing, crossing, crossing. There we go. All right, so same number of crossings, same alternation of over, under, over, except not really. So right, what's the difference between K1 and K2?
As you move from left to right, we start with an over at the top.
Okay.
And then we start with an under.
Yeah, so if we apply some kind of an orientation to these knots, right? And so this might be a place where you were asking before, will it help us to mark one point as an origin point for a knot? And that's generally no, but it can help for us to fix an orientation for the knot. So you're saying left to right or something. That would be a way of sort of specifying when we immerse a circle into 3 dimensions to create a knot. If we do that where the circle has an orientation, maybe the circle is oriented clockwise or something, then that's going to give an orientation to our knot. And from that notion of orientation, we can make a distinction between the 2 knots that we have here. They're the same number, the same alternation, but they're a different orientation. And what we'll say is that these are opposite knots, right? It's like 1 and -1, right? They have the same value somehow, but they have different orientation to one another. And so the question is, are these 2 the same somehow, or are they different? Well, they're both in some way, right? They have common features, but they also have this duality to them. But through this process, we discovered that K1 and K4 are in fact the same knot, because strongest possible terms, we can draw the same diagram for them. K1 and K4 are equivalent. K2 is the opposite of K1. And so, suggestively, we will write K1 equals minus K2. Okay, to denote the opposite of a knot. It's just you take every crossing in the diagram and you just switch over to under, and you get the opposite of the knot. And just by picking up this K2 and trying to fool with it, as you all did, you convince yourself that it's not in fact the same as K1. So here's a question. Is it possible to draw a knot which is its own opposite, which actually gives us the same knot when we reverse its orientation.
And the unknot.
Yeah, the unknot. Yeah, the unknot certainly, right? Yeah, the unknot doesn't have any crossings. So if we reverse all of its crossings, we get the same knot. Cool. What about any knotted knot? Can we think of a knotted knot that actually is the same thing as its opposite? I think we can convince ourselves that knots that have 3 crossings in their simplest presentation are all one of these two. Right? It's not really possible for us to make a knot with 3 crossings that's not either K1 or K2. Right? When we boil it down. And those two are not equal to their own opposites. So if we want something that's knotted, which is equal to its own opposite, we're going to need more than 3 crossings. So let's make that the next task. See if you can come up with a knot diagram with 4 crossings in it. Then we'll actually make it. I'm going to go get more rope out of my office. Make it, and we'll see if it actually is equivalent to its opposite. So the question is, can we find a knot which is knotted and which is equal to its own opposite? A knot which is equal to its own opposite is called amphichiral. It is equal to its opposite is defined as, this is a great word, for no other reason than just writing this word, I wanted to define it. Amphichiral. Chiral, by the way, is a word that chemists love to use, right? It means handedness. Yeah, amphichiral. It's a knot that's equivalent, it's equal to its opposite. And so the question is there a knotted amphichiral knot? And one of the parking lot questions is, does it have to do with whether the number of crossings is even or odd? So with 3 crossings, we decided that the answer was no. 4 crossings? Maybe. So that's our next task, is to find out whether or not it's possible with 4 crossings. Even odd matter, question mark. Cool. So one of the ways to think about how you made this knot is, again, we started with 2 crossings, one here, and it was an under followed by an over, so that we couldn't just slip it out. And then we took the 2 ends and joined them up with each other in a way that didn't go through this loop, because if we went through this loop, then this one on top would be boring and you could untwist it. But if you go through the top loop, now we can't untwist the top loop with a dull flip, and we can't untwist this part with a dull flip either. So this feels like the 4-crossing knot. It feels like a knotted 4-crossing knot, put it that way. Question is it the only one of its kind? If we flip it, if we take its opposite, do we get the same knot, or do we get a different knot? So the opposite would look like, this would become an over, and an over, and an under, and then that, and that. Right, come back up this way. Same knot, different knot. So really what this is it's just the mirror image of the other knot. These two are opposites. Chemists would call them enantiomers. Right? Just place it in the mirror. Can we convince ourselves that these are the same, in fact, the same knot? Let's try and help ourselves here by giving the various arcs in this knot a color. And by an arc, what I mean is one of these unbroken strands in my knot diagram. So there in red is one arc of the knot on the right. If I color this next strand green, that arc will end right there. Then I'll put a blue on the next one. And then I have this one last little arc that maybe I'll make yellow or something. So there are 4 arcs that make up this knot. And now if I just flip this over, we just have to see whether or not when my red strand, so now my red strand is going to be that one instead, right? My blue is going to move from the right side of my diagram to the left. My yellow is still right here. And the green goes around this side. all we really need to do is check to see that that the orientation of these strands when they cross one another still kind of remains the same, right? So at this crossing, maybe this one right here, I've got red crossing with, if I look sort of counterclockwise, I've got green on its left and blue on its right. And then here, it's kind of doing the same thing. Is this the same knot? If I read the knots from left to right as far as what the crossings are, we've got, for the knot on the right, an under, followed by another under. And then if I keep going around this side, it's another under, another under, under. Right? So these are just all, the 4 crossings are all unders. Under, under, over, under, under. Right? When I flip it, those all should flip, right? So that I'm going to have over, under, under, over. Did I screw something up? I feel like I must have screwed something up over on this side. Under, over, under, under. Did I draw the diagram wrong? Because then on this side it's over, under, under, over. So I screwed up my diagram. So what I'm going to do is I'm going to look at a different way. Maybe it's simpler for you to draw knot diagrams. I'm just going to draw it as though the crossings just go right over each other. So, and then erase, exactly. So, like that. And then I'll just go in for each of these crossings and decide which I want over or under. So for this one here, it used to be over going this way, so now I need it to be under, so this strand needs to remain unbroken. So I want to erase there and there. So that now that's that one. And the one on the other side of it needs to go from an over to an under instead, so that needs to break there. If I have that right, yep. And then going down to the strand on the bottom, here we have unbroken going from northwest to southeast. We need it to be the other way on this one, so we'll do that. Right, and then the one in the middle is unbroken, again going from northwest to southeast, so we need to break it in the same way. That may be a shortcut to drawing good knot diagrams if you have a good eraser, a very precise eraser. So okay, let's look again at the coloring of the arcs. Here is my red arc. My yellow arc is this little one there. My blue arc is now that one. And the green arc is this one. So what do we think? Same knot, or have we changed something fundamentally about the knot that we have here? Let's count overs and unders one more time, going from left to right. This is under, followed by an over, and then following the blue arc around, we've got an over and then an under, right? But then since every knot closes back in on itself, rather than listing them as just in a line like this, U, U, O, O, U, really it's more like U, O, O, U, and then it repeats, right, as we go around the circle. I mean, that's maybe another way that we could represent how to contain the information in a knot. But then if we reverse all of those crossings, the unders are going to change to overs, the overs are going to change to unders. But when I go around in that loop, I'm saying the same number of crossings in the same order.
So if we don't really define a start-end point, you could just rotate.
Right, exactly. It doesn't matter. We could just take these little sort of what we would call cyclic orderings of crossings and just continue. They're the same cyclic order, right? A pair of U's followed by a pair of O's. That makes these two the same knot. So in fact, this knot that you sketched with 4 crossings, in fact, is the only knot whose lowest terms diagram has 4 crossings in it, is amphichiral. This is equal to its own opposite. And because it's one of these simple building blocks of knots, we also give it a special name. We call it the figure 8 knot, for I think obvious reasons. That it has that snowman feature that many of you identified in our first exercise today, but that it actually does end up being knotted because we pass that strand through a part of the snowman that lets us not untwist the dull loops in the diagram. The last question about this knot is, what if we looked at changing all the crossings from overs to unders and vice versa when we take the opposite of a knot. What happens if we just change one crossing? Let's suppose that I pick one of the crossings in this diagram and I switch just the one from over to under. What's that going to do to my knot? So what happens on this figure 8 knot if I just change one crossing? So let's change this so that the bottom crossing is, instead of an under, it becomes an over. Over, over, under, over. And let's see what knot that would give us. So then this is going to come around this way. All right, let me fix the crossings. So we didn't want to change the one on top. We didn't want to change the one up here. We didn't change the one in the middle, so it's still this. But we changed the one on the bottom so that now it looks like that. Right, yeah, so what's going to happen? What dull maneuver do you want to do here?
The over.
These? Yeah, this over here, we can just yank over to that side, right? So that's one of our dull maneuvers. So let's do that, and then let's trace the consequences.
Oh, yeah.
Yeah, how about that? So now this goes here, right? And then this connects. Now we're down to how many crossings? 2. And each of these crossings can then just be untwisted, and we end up with an unknot. So that's interesting. Just switching one crossing gave us an unknot. And that's one of our last definitions for the day. We call that the unknotting number for this knot. Is how many crossings, what's the minimum number of crossings that we need to switch to unknot my knot? Switch just one crossing to unknot the knot. Right? It doesn't mean that any one that I pick to change is going to unknot it, but it does mean there exists one, that just changing that one unknots the whole darn thing. Right? And unknotting numbers can be tricky to find for knots that have bunches of crossings, because you might never know if you have the minimum number. All you can know is that you've done better than your last guess, if it happens to be lower. So one of the main themes of the semester is about representation and invariance, right? And the question is, we know that 2 different diagrams can represent the same knot. That was one of our key discoveries today. Can represent the same knot. And so the question is, what differences matter and what differences don't? What differences in diagrams actually give us the same knot versus different knots? And so we call them dull. The dull differences that give the same knot, that leave the knot unchanged. There's a lot of things we could do to a diagram, but the 3 that we identified today are the building blocks of all of them. And that's an important theorem in knot theory. Are all, this is a theorem, built out of the 3 that we looked at. And here's the diagram of those 3. This diagram came from Wolfram's Math World website. The 3 moves that we can do to a diagram that leave the diagram different, but they leave the knot the same, are all built on a foundation of these 3. These 3 are called the Reidemeister moves. Reidemeister, of course, named for the person who proved the theorem that's being alluded to here. And when we refer to them, we'll call them type 1, type 2, type 3 if we're being fancy. Or if we're being less formal, we'll call them the twist, the poke, and the slide. Right? The twist was this one that had the power to change our number of crossings by 1, reduce the number of crossings by 1, right? The poke, or the unpoke, I suppose, reduced our number of crossings by 2. And the slide actually doesn't do anything to the number of crossings, right? And the surprise in the theorem is that these 3 describe everything that we could possibly do to a knot diagram to leave the diagram the same. If there are 2 knot diagrams that we cannot relate together by a sequence of Reidemeister moves, then those knots are different. Right? So that's the real power of the theorem, is it tells us the extent to which diagrams are faithful representations of knots. Right? That it's true that diagrams can be different for the same knot, but they must be different in a combination of these 3 ways. Right? And that's it. Any other difference which we can't represent by a series of these Reidemeister moves must mean that the knots are different. So to set the stage for next time, today we just took a flyover of what knot theory is. What are the kinds of questions that we can ask and answer in knot theory? The primary one for now being, how do we represent a knot in a way that's faithful, in a way that's invariant? What invariant thing can we associate with a knot from which we can recover the knot, right? And today, that invariant was diagrams. Right? Modulo the Reidemeister moves, which leave the diagram different but the knot the same. If we forget about Reidemeister moves and reduce every diagram to its simplest form, its lowest terms, then at that point, we have something which uniquely characterizes a knot. 2 different knots will have to have different lowest terms diagrams. Right? So that's our first invariant. It's not a very algebraic arithmetic, we don't have our hook really yet into algebra, other than this sort of suggestive notation of a knot with its opposite, the unknot being a 0. That's a little suggestive, but not quite to the algebra step yet. So how we're going to get there is to come back to the diagrams on this slide. When we finally realized that K1 and K2 were different knots, they were very similar but not quite the same, the way we did it is we put these 2 diagrams into a standard position where we stretched these 2 strands here to be parallel, and all the twists sort of were collected into the middle. So where we'll go next is we'll focus on those twists. And by cutting these knots in those along the parallel strands, so if I just sort of cut this part and cut this part of K2, for example, and I can imagine just sort of fixing those 4 endpoints, what we get is no longer a knot, right? Because it's not in a circle that we're embedding. It doesn't join in on itself anymore. But it's still an object that we're going to be able to study. It's called a tangle. Specifically, it's called a 2-tangle. It's what we get if we take 2 strands, basically, and between 4 people hang on to the ends of each pair, holds on to the ends of 2 ropes, and then does something to twist those ropes together. And then what we get is one of these tangles. And so what it does for us is it kind of lets us focus in on twists and crossings as the building blocks of knots later on. And it's going to give us our first taste of how to come up with an invariant, a thing, a mathematical object which describes a tangle, which is not a diagram, but which actually has some arithmetic associated with it. So the real surprise is that every one of these tangles is going to be classified by a rational number, a fraction. If I give you a fraction, you should be able to build me a tangle in the same way that anyone else would if they got the same fraction. Right? And vice versa, to every tangle, we can determine what fraction it is that represents that tangle. And I'm using the word fraction here to specifically, again, mean rational number. So integer on the top, integer on the bottom. Could be positive, could be negative, could be 0. You might imagine what a 0 tangle looks like. We'll also have an infinity tangle in there, which just is kind of like a different kind of 0 in a way. But then the real fun comes when we realize that rational numbers have arithmetic. We can combine rational numbers together. Addition, subtraction, multiplication, division, reciprocals, all that stuff. And because every one of these tangles is associated with a rational number, we can also do arithmetic with tangles. And that the 2 of those need to be intertwined. They need to be able to tell the same story. Right? So we need to decide, what does it mean to add 2 rational numbers together? What happens to the tangles that are represented by those numbers? Right? So that's where we're going next. So we're going to start our next class by getting started with tangles, figuring out how the arithmetic works, how it has to work based on our understanding of how tangles get twisted up. So that's where we're headed in our next class.